I'm Sally Lord. I'm doing my PhD at the University of Oxford, and today I'm going to present some work that was done in collaboration with the Institut Jean Lamort in Nancy, France. And this work is on the characterization of noncollinear exchange-coupled trilayers of epitaxial cobalt manganese silicon and chromium for Magnonic applications. So to start with, I'm just going to give a bit of an overview of Magnonics and what this field is, as this is kind of the motivation behind our work. So Magnonics is a field of research that focuses on understanding and exploiting the properties of magnetic materials in order to develop them for novel computing applications. And Magnonics is based on spin waves, the quanta of which are magnons, which is where the field gets its name from. And spin waves are just the collective excitation of the magnetic order of a system. So in the Magnonic computing paradigm, information is encoded in the phase and amplitude of these spin waves, and therefore as they propagate throughout the system, information is also transferred. But in order to develop Magnonic computing devices, we need to find materials that are suitable for these applications. So historically, most of the research has been focused on YIG, or yttrium iron garnet, because it has a really low Gilbert damping parameter and therefore long Magnon propagation distances. But there are some drawbacks to YIG, even though it appears to be the most ideal candidate. And these kind of include the fact that it has a complicated fabrication process, and also as it's an insulator, it currently can't easily be integrated with CMOS, which reduces the kind of commercial viability of YIG. So recently, more research has been done into kind of investigating other types of magnetic materials that could be suitable for Magnonic applications. And one kind of material that's received a lot of interest is antiferromagnets. So these are a type of magnetic material where its adjacent spins are aligned antiparallel. And they are really interesting for Magnonic computing applications for two reasons. Number one, they have two non-degenerate modes, which means there is an additional degree of freedom with which you could encode information. And number two, their frequencies in the terahertz range, which is really good for computing because it would enable faster writing speeds. But it's actually also the main drawback to antiferromagnets because terahertz frequencies are very difficult to excite. And therefore, it's difficult to integrate them with existing CMOS technologies. So the question is it possible to find a material that combines these advantages without having the disadvantages? And the answer is yes. One potential material candidate could be exchange-coupled trilayers of the Heusler alloy cobalt manganese silicon. But what are exchange-coupled trilayers? So exchange-coupled trilayers are consist of two ferromagnetic layers with an interlayer sandwich between them, and by controlling the thickness of the interlayer, you're able to control the coupling between the two ferromagnetic layers. So for certain interlayer thicknesses, you're able to excite two non-degenerate exchange-coupled Magnon modes, and these have frequencies in the gigahertz range. But obviously, this kind of structure type of material is not very useful, is only useful for Magnonic applications if you have a good choice of ferromagnetic material. And so one choice that could be good for Magnonic applications is this Heusler alloy cobalt manganese silicon, because it has a number of properties that would make it advantageous for Magnonic applications, such as the high spin polarization, the low Gilbert damping, and it's also metallic, which would mean that it's easier to integrate it with existing CMOS technologies. So in the following slides, I'm going to present our study on the exchange-coupled trilayers of cobalt manganese silicon and with the chromium interlayer. So that takes me nicely on to the next slide, which is where I'm going to discuss the sample fabrication. And this sample fabrication was done in the Institut Jean Lamort. So in this work, we fabricated 18 different samples with varying chromium thicknesses. And the reason that we were interested in varying the chromium thickness is because it's this interlayer thickness that determines the magnetic properties of the trilayers. So the samples were grown by molecular beam epitaxy. And first, a buffer layer was deposited on the MgO substrate to provide a homogeneous surface. Then the first cobalt manganese silicon layer was deposited at the temperature of 350 degrees and then annealed in situ to improve the chemical ordering of the Heusler. Then the chromium interlayer was deposited at room temperature. After this, the second cobalt manganese silicon layer was deposited at reduced temperature compared to the first always the layer, and this was to prevent interdiffusion between the cobalt, manganese, silicon, and the chromium. And then finally, a gold capping layer was added on the top to prevent oxidation. And the epitaxial structure of these samples was verified using the transmission electron microscopy measurements. So after we'd fabricated samples, we then wanted to characterize the magnetization, the static magnetization properties of the samples in order to extract some information about the exchange coupling between the trilayers, between the two ferromagnetic layers. So the magnetization characterization was carried out using a squid BSM magnetometer. And for all the measurements, the magnetic field was applied in plane along the easy-like axis of the cobalt manganese silicon lattice. And here on the right in this figure, you can see the magnetization loops for a selection of the samples for various different chromium thicknesses, chromium interlayer thicknesses. And I think what is clear is that the thickness of the chromium really affects the magnetization behavior. So you can see that for like these pink and green loops, which correspond to about 0.873 and 2.619 nanometers of chromium, you have this highly rounded magnetization behavior that's not seen for some of the other chromium thicknesses. And we've also observed large saturation fields of the order of half a Tesla, which is about 10 times greater than the saturation field that's measured for a single film of cobalt manganese silicon of the same thickness. So clearly varying the chromium thickness is having effects on the coupling behavior of the trilayers, but how do we quantify this? So in order to quantify this exchange coupling behavior, we moved to simulations. So we simulated the magnetization loops by numerically minimizing the total energy expression. But in doing this, what we were really interested in was the exchange energy term, which is governed by these two constants, J1 and J2. And J1 is the bilinear coupling constant, and J2 is the biquadratic coupling constant. And what we were really interested in working out was which type of exchange coupling is dominant in the system. Are we seeing more bilinear coupling or more biquadratic coupling? And in order to work this out and sort of quantify it, we simulated magnetization loops and then fitted them to the experimental data. And what we found was that there were multiple values of J1 and J2 that minimized the energy expression. So you can see here, there's a large range of values of J1 for a smaller range of values, but still there's quite a few values of J2 that minimize the energy expression. But then we took these values of J1 and J2 and we simulated magnetization loops with these values of J1 and J2, and you overlaid them on top of the data, and it looks pretty awful. It clearly doesn't fit. So then we were like, okay, why is that? So we went back to the data, the experimental data, to see if there was anything we could extract from the squid data to give us more of an insight into what the dominant coupling mechanism was in the system. So we went back to the squid measurements and we extracted the magnetization at 5 millitesla because we thought this would be a good indicator of the dominant exchange coupling mechanism. And the reason why it would be a good indicator is because depending on the magnetization at zero field, it would be different depending on whether you had predominantly bilinear coupling or predominantly biquadratic coupling. So the magnetization at zero field for the two types of coupling is given by these values here. So we extracted the magnetization at 5 millitesla, and here is plotted the relative magnetization, so that value divided by the saturation magnetization. And this gray line here is this value that you would expect if you had dominant biquadratic coupling. What you could see is that for the range of chromium thickness values, the magnetization at 5 millitesla, the relative magnetization at 5 millitesla is close to this value, which kind of implies that perhaps biquadratic coupling is the dominant coupling mechanism in our system. So we went back to the simulations and we fitted the magnetization loops to the data again, but this time we set J1 to 0 and we only fitted the J2. And you can see that the curve is much better when you set J1 to 0. The fit is much better when you set J1 to 0 and only fit J2. But still, we were unable to reproduce this curvature that you see, this nice curvature that you see in the experimental data. And it's unclear where this curvature arises from. It could be due to some sort of chiral term, but we are still investigating this. It's unclear if there's a physical basis to this. So anyway, we ran this fitting program for all the samples, and we extracted the biquadratic coupling constant for all of the samples. And here you plotted the biquadratic coupling constant J2 versus the chromium thickness. And what you can see is that the strength of the exchange coupling oscillates as a function of the chromium thickness. There's sort of two periods. And you have a peak in the exchange coupling around 1.45 nanometers. And yes, so for most, there's a large range of chromium thicknesses where the biquadratic coupling strength is large. So in conclusion, in this work, we fabricated a very nice set of samples of cobalt, manganese, silicon, chromium trilayers using molecular beam epitaxy. We characterized the magnetization using squid BSM measurements, and then extracted information about the exchange coupling behavior using simulations, but also experimental results, and found that in the system, the dominant exchange coupling mechanism is biquadratic. Yeah, but there are still some questions outstanding. So, for example, where does this curvature, these highly rounded magnetization curves come from? Is this due to some sort of chirality that we haven't yet been able to confirm? And we would also like to investigate the dynamic properties of the couple magnon modes in the future. So yes, thank you very much for your attention. I'm happy to take questions. I'll leave the slide.
Sally, thank you very much for your excellent presentation. We have one question in the chat from Maria. So how sensitive are the properties you have measured regarding the stoichiometry in CO2 and CI layers?
Sorry, could you repeat that? I can't. Oh, I can maybe see the chat. I couldn't hear you.
Do you see the question on the chat?
Let me have a look. How sensitive are the properties you've measured regarding the stoichiometry in the that is a good question. So in answer to that question, all of the samples that we measured had very good stoichiometry. So the MB setup that we used was able to have very precise growth conditions. So I'm not sure how sensitive the properties are because we only measured samples that had almost perfect stoichiometry. Yes.
Okay, thank you. And the next question we have, it's why have you chosen the growth temperature around 300 degrees Celsius degrees? Could you elaborate a bit on that?
So this is the growth temperature of the Heusler alloy. So again, the research group in Institut Jean Lamour, where we fabricated the samples, they've got a lot of papers on fabricating Heusler alloys, and they have just done a systematic sort of, they tried multiple different temperatures and found that this was the temperature gave the best growth conditions.
Okay, thank you very much for your presentation and for answering